Good afternoon. Welcome to the course Thermodynamics of Materials, the lectures 75 and 76. So, last class was lecture 73 and 74, and that is about 8 months before. The last class was on March 21, 2024. Okay. So, anyway, we will actually continue with the same topic, namely phase equilibria. Maybe we will be able to finish that topic today. So, some so we'll first additional points. We may call corollaries. We may talk on corollaries or say some missed out points like this, additional points. So first is, so maybe 6 or 7, one by one. First is, if you recall, this was the last line, or this was the relation that we got. I'm like copying, this was the relation, vapor pressure temperature relation. Recall. Vapor pressure temperature relation, delta Cp is a constant for a case that delta Cp is a constant, non-zero, neither a function of temperature, only a constant. Okay, we call it delta A perhaps. Delta is called this. This is all discussed before. So what is the relation? This I am writing once more. I am copying this. ln P is the vapor pressure, is minus quickly, is minus delta H298. Okay, well, you can consider this. Okay, this is written anywhere. You consider a liquid to a vapor. This is the process. The phase equilibrium, single component phase equilibrium. Minus 298 delta A. This was already in the note. You may see last class maybe. You see this? Divided by R times 1 by T plus delta A by R ln T plus Z. Z is a constant. Answer. The relation, so no problem. This was already done in the class. I am just copying only. Is a constant. Is a integration constant. As we call this, is a constant. Sorry, is a constant. Does not waste time. Okay, I am just want to say this. This is actually, see, these are all constant. These all constant. So it is actually, let me write A plus B by T plus C ln T. This is the standard form. In this form, we have got this. Actually, I wanted to mention. I forgot. This is the A. A is the here constant. B by T. These are all constant. See, delta H290 is a specific value, and you see, and okay, and delta A is a constant. Delta Cp is a constant, namely delta A. Let's say 3.4, 2.3. So this I missed. Those it is actually additional points are missed out. This form. This will be useful in the assignment problem. Okay. So this form A plus B by 2. See. Next is thermodynamic interpretation of phase equilibrium, of any phase equilibrium, namely Eg is equal. Let us consider this Eg I in the alpha phase goes to I in the beta phase. I alpha to I beta phase transformation. Clearly, solid liquid. Okay, okay, you know this very good. So what I'm trying to tell you is these are the thermodynamic interpretations maybe. This is what are the criterion, you know, GI in the alpha phase, Phi is sameness of Phi equal to, from delta G is 0 at equilibrium. In phase equilibrium, but this is equilibrium. GI alpha is GI beta. Not only these, others also there, like fugacity. Fugacity of I alpha is fugacity of I beta. What else? Activity of I alpha phase in the alpha phase is the I activity of I in the beta phase. And what else you can say? Another still another vapor pressure. Pi alpha is Pi beta. So here P is the vapor pressure, right? Where P is P is vapor pressure. Vapor pressure. Fugacity and pressure, vapor pressure, you know, fugacity and pressure are activities are what with respect to same standard state. Activity always has a standard state, same standard state. These are the thermodynamic interpretation. This is coming from delta G is 0. Recall, coming from source relations. I tell you what, you are all actually, these are nothing new. All you can derive actually. What is this? Source relations is what? dg T is VdP. Recall VdP minus SdT. Then under constant temperature is what? That was the very beginning. RT d ln fugacity. Then what? It went to RT d ln A. These are obtained from this. Okay, and is also RT d RT d ln vapor pressure. P is the vapor pressure. This is the vapor pressure. Okay, A is the activity, you know, fugacity. You understand this is activity and fugacity. So this one, and also and delta G is 0 at equilibrium. If you utilize this, you will get, you have already obtained. So like this you already obtained. So from this actual fugacity also equally, so many equalities simultaneously hold good when equilibrium is, phase equilibrium is there. Like fugacity equality, vapor pressure, activity, and free energy. Of course, free energy that is your third. This is actually second point that actually I wanted to tell you. Okay, over. G versus T and G versus P plots for a single component system, or a single component system, e.g. water, because it is very easy to follow. We call just note the normal boiling point, BP for boiling point for water. Normal boiling point is hot for water is 100 degree centigrade, which is nothing but I'm sorry, let us melting point, it is better. Normal melting point, I'm very sorry. Melting point is 0 degree centigrade. Is 273 Kelvin. Sorry. Okay. This is normal melting point is 0 degree centigrade. Normal melting point. You know what is the meaning of this? There are infinite melting points. Normal is actually the just special one. That is actually when the external pressure is 1 atmosphere. The melting point corresponding to 1. Okay. Normal melting point. That's similarly normal boiling point. I take this only. So what I want to tell you, the sketch will be helpful. Not bad for water system pressure. Water system, you know, has a speciality that this goes this way, no doubt. Then it is tilted leftward rather than rightward. Slope is negative, and this is water. This is ice is solid actually. Ice, that is solid. Ice, solid. This is water, that is liquid. This is the water vapor. So you see, I'm sketching. See, or you see, give this. What is this? Normal melting, that's the melting point at 1 atmospheric pressure. So select 1 atmospheric pressure somewhere. 1 atmospheric pressure. And what is the temperature? This temperature? Just schematic. What temperature this is? Must be 273 Kelvin. There, this is your so-called melting point or freezing point. 273. This is T Kelvin. P atmosphere. Okay, this is P atmosphere. Now I am plotting. You follow this. You show this phase equilibrium. How? G versus take one by one. You are plotting what? Let me tell you. You are plotting of G of water, G of ice, G of liquid phase, G of solid. Pure. All pure you are plotting. So one by one. For a given pressure, P is fixed. Namely, what value you have fixed? Obviously, to your choice is 1 atmosphere to your convenience. Plot G against P fixed against temperature. You know dG is VdP minus SdT. Since pressure is fixed, it is governed by dG is minus SdT call. dG is VdP minus SdT. So when it is gone, so is dG constant pressure is minus SdT. Everyone knows. So for plot this, so if I plot for a solid, means ice, G versus T will be what? What is the slope? What is the, this will be curve actually. What is that? What will be this curve versus slope will be what? Signify what? Entropy. Entropy, you know, is a positive stuff for all this. It's positive, but negative sign is there, so it will be negative slope. So, and so I am drawing this first. This help you. This help you. One is steeper, one is flatter. Which is steeper? Which has more entropy? More negative. Which has more entropy? You know, solid and liquid is liquid more entropy. So this must be for liquid. Means ice. Liquid, and this is for solid. I'm very liquid means water. Water. I'm very sorry. And solid means ice. Sorry, liquid is sorry. Okay. So water. Well, you write here. Water liquid to water vapor. You may write here. In this equilibrium, water liquid to water vapor, solid to liquid. Water solid to water liquid equilibrium. Equilibrium. Right here. Don't worry. So what is this temperature? You understand now? This is temperature where the free energy is same. That means at this temperature, this is nothing but the so-called melting point of 273 Kelvin. This is the thermodynamic interpretation, Gibbs energy interpretation of melting point. Okay, this is the melting point. You can very easily check now. Quickly check. Okay. Now remember, right here, somewhere right. Entropy of liquid is greater than entropy of solid. Right? Is it better? Right? Liquid means water. So right here, liquid is water. If it helps you, solid is ice. Now check quickly. If we increase the temperature, which is stable? Here, who's stable? This is the coexistence. Both have same free energy. That is the perfect equilibrium. Both together. Both together. Any temperature higher than this, which is lower, liquid. See here also, giving the pressure. If we increase the temperature, see this is landing into the liquid stability region. This is okay. And similarly, obviously, the opposite is actually if you lower the temperature, ice. Means solid is a lower free energy. Over. This part is over. Next, alternatively, is what I will remove this letter. Again, what is the alternative sketch to show this? Nothing but instead of pressure fixed, temperature is fixed. We fix the temperature at what? Namely 273 Kelvin already. So pressure is now variable against G. Ge versus P. What is this? Remember, what is the relation here? dG at constant temperature will work. Now this is a constant temperature. Temperature is fixed. So is minus VdP. I am very sorry, VdP rather, VdP. Now tell me, if you plot, what is the curve like? dGdP is given, this slope is given by the volume. And you know volume, whose volume is greater? Typically liquid has greater volume, but this is anomalous situation. Water is an anomalous situation, so volume of solid will be greater. volume will be greater. So and positive slope. V is volume. So this will be like this. So let me draw this. One is this, another is this. Schematic will be very helpful. So this is for what? Volume is greater for, as I told you, solid means ice. Solid. Ice. This is liquid. Slope, steeper slope, flatter slope. This is liquid water. What is this intersection point corresponds to? What does this corresponds to? Tell me. What pressure? Temperature is what? Pressure is varying just 1 atmosphere. The normal melting point means normal means 1 atmosphere. Melting point at 1 atmosphere. Normal means reference to 1 atmosphere. Normal is 1 atmosphere. Recall. Infinite melting point. Say any curve? Infinite. All infinite. Only one is corresponding to 1 atmosphere is special name. Normal. So what is this? What shall I write here? This is nothing but what value it is? 270 degrees fixed is 1 atmosphere. So 1 atmosphere, let me write, no problem. Over. Now check again check with this diagram. This time see temperature fixed, so temperature this fixed the temperature. Now if you increase the pressure, this is the point where P and G same, means coexist. Means this equilibrium is struck. Both have same heat energy. So this is a coexistence. But if you change the pressure, then there is elimination of phase. Which one will be eliminated from this? Say high energy will be eliminated. Okay, so what is this? If you increase the pressure, water will be stable. Let us see. If I increase the pressure, which is stable? Lower energy is what? Liquid means waters. Again, you see, if you decrease the pressure below this here, which is stable? Solid is the stable. Ice is the stable. So if you decrease the pressure, which is lower? Solid is lower. This is the diagram actually that you can have. Next is some Trouton's rule. I write here. I use this space. 4th point. Trouton's rule. 2 rules. Sometimes okay, you are asked, well, do you know Trouton's rule? So what you will say? So let us touch upon this. Trouton's rule and Richard's rule. Not very, I would say, very important, but sometimes, when you don't have data, this says Trouton's. Okay, I should write Trouton's rule. Trouton's. What is it? Molar entropy of vaporization. Molar entropy, write this Trouton's. Molar entropy of vaporization at normal boiling point. Normal boiling point is approximately 88 joule. Data, in fact, it is joule per mole, as you know, joule per Kelvin rather first mole. Right here for most metals. Metallurgists for metals. Most metals are metals. For metals, right here nicely, for metals. Okay, this is. So what does it mean? Actually, it says delta S, that is delta S liquid to vapor. Metal iron liquid to iron vapor. Zinc liquid to zinc vapor is how much it is. It is actually, say you may write delta S0 way better. This delta to be specific. Delta H0 liquid to vapor by the normal boiling point. TB is become normal boiling point. Okay, boiling point simply normal boiling point. Okay, so this is okay. So very good. So now what happens here? So from if you know boiling point, the boiling point, then actually you can get the enthalpy of transformation. If it is, say suppose it is 88 multiplied by the boiling point. Boiling point you know actually, boiling point actually, melting point, boiling point data. So if the boiling point known, then you know the enthalpy of vaporization. Molar enthalpy of vaporization, molar entropy of vaporization is typically this value for most metals. So this is okay. So this is okay. Now if you get entropy, then what's the gain, sir? You get this. So that means you can write delta S0, you know, liquid to vapor. Achha, how do you get this? Why this is this? By the way, this is a good question, that why it is this, sir? Delta G0, recall quickly. Delta G0 is what? Liquid to vapor. Is delta H0 liquid to vapor minus T delta S0 liquid to vapor. Now see this. What is this value? As a normal boiling point, okay, 0. You say the sameness about the free energy. So that normal standard state, vapor is standard, liquid is pure, single phase is pure. So delta G0 is, this is 0. Sorry, I'm running out of 0. It is 0. So if it is 0, I should change. It is 0. It is 0. So 0, that leads to that, since recall, since you get this, I don't write any anymore. So this gives you this relationship. So what happens here? So you get this both the data, then you can actually write yourself the energy expression. You don't have to consult books in case you are out of actually data. You don't have access to the data book. Then you using this, you can always get. How will you get this? You can tell me what is the relation general delta G0. Now once you know this, so shall I write? You know this TB is known, so is delta G, using the relation. So delta G0 liquid to vapor, you can always just look at books, you will get this. Suppose you don't have, then this is the resort. Delta G liquid is delta H0 liquid vapor minus T delta S0 liquid vapor. So you know this, so delta G0 liquid as a function of A plus BT, a constant A plus BT form delta G0 you can generate yourself, you don't have to data. So this is about the liquid and vapor, so liquid vapor equilibrium, right? I have written. Similarly, star this point. Similarly, Richard's rule. This I will not explain much, but only I will say Richard's rule is what? Is about solid to liquid melting point, about the transformation melting point. So what is molar is what Richard's rule? I am just giving short melting. Delta S0 solid to liquid. Solid to liquid transformation, you understand, melting. Molar entropy of melting. So right, molar entropy of melting. Let me write this. Molar entropy. Entropy standard here because it is melting. This is about melting point. Is what? Tell me, you can tell similarly. Tell me what it will be. Delta similar argument. Delta is 0, solid to liquid. Okay. Then what is TB? Instead of TB, it is TM, melting point. Okay. This is roughly is approximately 9 joule per Kelvin per mole. Thank you. So these two I touched upon because in case you are running out of data, you can generate the data. That's it. This is entropy, you know. At equilibrium delta G is 0. So one you know about of the three, one you know the standard value and delta G is 0 at equilibrium. So delta is also. So this is the third point, fourth, fifth. Can I remove this? Oh, so I think this will be easier. Fifth point. Fifth point is what? I tell you. This may be easy for you because you have, but you just concentrate on this. And this means this you have come across already, maybe because in a phase. What is this called? Phase physical metallurgy. So what is this? Phase equilibrium application. Phase rule. I am very sorry. Phase rule, also degree of freedom. Degree of freedom application. Phase rule application to the single component, the single component phase equilibrium, component phase diagram, phase equilibrium, obviously phase diagram. Phase diagram is always, phase diagram is equilibrium diagram. Phase diagram is equilibrium diagram. Phase diagram, phase diagram or phase equilibrium. Phase diagram or equilibrium diagram. Okay. Equilibrium diagram. So I'm just, can I remove this? This part also I should remove. All over. So 2 more points. Slowly, let us go slowly. Huh? This is all. I'm just sketching for you. This so that it helps you. So I'm writing typical system. Solid, liquid, vapor. Okay. Degree of freedom. I'm writing here. See, you see, you give a name to this. You remember what I gave a name is OA prime. Recall OA prime. This will help. OB prime, OC prime. These 3 curves. The equations we developed in the class. We developed this. Okay. So quickly. So OA prime, solid, liquid, curve. I'm repeating all these diagrams are always. You keep on drawing actually. This is normal. This is unusual. Abnormal. Water system is abnormal system. Unusual system. So anyway, a single component is what. Stability, apply the phase rule. Case 1. What is this? In the stability region, in the single phase stability region, that's right, the single phase stability region, the single phase stability diagram. Remember, phase diagram or equilibrium diagram or stroke, equilibrium or stability diagram, all same. Stability diagram. All same, okay. The single phase region, namely, can you tell me? Like, e.g., solid region is this one, or liquid region, not line, curve. Region means 2-dimensional. Solid or liquid or what is it called? Vapor. Single phase. What is the applied degree of freedom? So F is C minus P plus 2. What is the component? This is a single component system is 1. Namely, say metal I. So 1 component. How many in the single phase? Single phase I have said. So phase is 1. Here, so you apply here. Say apply to this place. The liquid stability. Liquid stability you are analyzing through phase rule as it. So 1 minus 1 plus 2. So you have 2 degrees of freedom. What are they? Means if freely here temperature pressure. Oh, very sorry. Temperature. Very sorry. Pressure, typically pressure on the y-axis and temperature on the x-axis. So you freely choose. You freely fix, freely choose, freedom. So 2. So temperature, pressure both. How, sir? So for just consider liquid, easy. So I choose any randomly, freely, independently. As I choose this place. Then what temperature? See, I can choose this. Suppose this. I'm not actually just glossing over it. This. This is the pressure I can choose. I can choose this pressure. Liquid still stable. This pressure. So I fixed. I'm sorry, temperature. This temperature. The range of temperature. I have a choice on that. And this is also initially it was a choice. Pressure is this. I could have chosen this one. So both are freely. This is 2 dimension, 2 degree of freedom. Temperature, pressure. You write here 2 dimension means 2 dimension region. 2 means 2 dimension. So this is a 2 dimension. Okay. 2 dimension. Region. I say 2 dimension region that has 2 dimension. 2 for 2 dimension. 2 dimension situation. 2 dimensions. Say 2. One is 2 dimension. In contrast to case 2. This is over. So you can choose. Similarly, you apply this. The 2 phase region. 2 phase regions. What are the 2 phases? Not single phase. Quickly. What are they? Solid, liquid. Right? Solid, liquid or tell me liquid vapor or solid vapor, namely solid liquid which curve? Curve OA prime. This is which curve? Liquid vapor OC prime, solid vapor OB prime. You check this again. Yeah, similarly, two phase. This the whole diagram is equilibrium. This is a single phase equilibrium. This is a two phase equilibrium. This is a three phase equilibrium. Whole diagram is equilibrium. So AP is what? C minus P plus 2 again. What is the C? See, single component already 1. How many phases this time we have considered? Two phase. Two phase equilibrium we have considered. So 2 is what? 1. That means one dimension. What is one dimension? A curve is a one dimension. Line is a so area is 2 dimension. Okay, that's it. So this refers to one dimension. And what is this? So what is the nature? It will be a curve. And what you choose here? Temperature, pressure? No. You careful about this point. So either T or P, not TP and P. T or P, one of them. Fix one, other is automatically. Fix any one, the other will be automatically fixed. Automatically is highlight this. Other one will be automatically fixed. This is about the degree of freedom. Automatically fixed means you have no choice. Automatically under fixed. So quickly demonstrate, quickly, very easy. Demonstrate here. Suppose you fix, consider liquid vapor equilibrium. So you have a choice, temperature, pressure. Suppose you start temperature. Oh, this is my chosen temperature. So you come here. So hot pressure, you have no choice. Only this pressure. It cannot be this or that. If it is this, then you will land into the liquid phase region, single phase equilibrium. It is a two phase equilibrium you expect. So this is the, shall I remove this? This one I should remove. Looks clumsy. This is actually, so this is one dimensional, so this is a curve, right here, curve. Here the two dimensional, right? Area. Previously area over area, this is curve. Is okay. What else I want to conversely, you can consider if fixed pressure, then to have the coexistence of liquid vapor, how many temperature possibilities? Only one. Means automatically. You have no choice. If you want to show your choice or freedom, then show another one. Except suppose this is a pressure. This is a corresponding temperature. Choose another one. The moment you try to, you are trying to exercise your freedom, but over exercise, then allowed by the phase rule. So then what will happen as a result? A phase elimination will take place. Okay. So this is the one that I wanted to tell you actually here. So third, let me finish this first. I may have some discussion here. I'll discuss this later on. Come back. Third, quickly. Three phase. What have written? Two phase region. Two phase equilibrium. Single phase region. Single phase equilibrium. Right? Sorry. Don't write. Single phase equilibrium. Please change this. Two phase equilibrium. The entire diagram is actually a phase equilibrium diagram. What do you want? The three phase. Quickly, what it is? AP is C minus P plus 2. Quickly. Plus 2. What is the component? 1. How many phases? 3 should be together. And 2. What is 0? What does it mean? What is the significance of this? 0 means you have no choice. Automatically fixed for you. This is the only values. These are the values. So this is called triple point. No choice. No independent choice. Pressure, temperature automatically fixed. This is called this point. This is what? How many dimension? Zero dimension. Which is that point? So 0 dimension. This is given by a point. This is usually known as triple point. Because three phase meeting, this is also known as triple point. And if you are interested for your actually just to note for water system, triple point value I am giving you, that helps you. Triple point is a triple point system. At triple point temperature is what? Pressure is what? If I recall, 0.00, I'll correct, I'll take this, 0.007 degrees, and let me check. This is what? 0.006. One is 0.006 to 0.075. Let me write first. 0.0 should be, this is atmosphere, no doubt. This is Kelvin. Just check, yeah? Let me check, yeah? Let me check on this. Triple point I have wrote somewhere. Forgot. Just 0.0075 centigrade. You can convert into Kelvin, okay? And 0.06 atmosphere, perfect. This is the triple point values for water system. These are the discussions that I wanted to make on the point. Which point I was discussing? Fifth point. Good, very good. 6th and 7th I'll discuss. Okay, you just follow me. This is slightly. Actually, I will have some critical discussions, critical issues. 6 months, one critical issue. 6th, one critical issue. Then I will consider stable, metastable last. Then this discussion will be over. One critical issue. You just concentrate on this. Concentrate on this. Call it figure 1. Call this figure 1. Retain this figure. Refer to figure 1. Refer to figure 1. Though it is actually, suppose this is actually figure 1. Okay, refer to figure 1. Achha. Wait a bit. One critical issues, refer to figure 1. If I refer to figure 1. This is all for what it will be. Refer to figure 1. Achha. Figure 1. Let me draw this. Otherwise, I am not feeling at ease. Water system discussing. Water system discussing, but the principle same. Right? Solid, liquid, vapor. Water system. System water. System water. Single component. System water. You tell me what is the significance. See, in this liquid vapor, again give a name. OA prime, OB prime, OC prime, no problem. Please consider pressure and temperature. I am asking you, along OC prime curve has how many degrees of freedom? Has how many degrees freedom? 1 degree of freedom. 1 degree freedom. So, for example, I fix EG, we fix temperature as what temperature? I tell you what, 69 degree centigrade, which is 342 degree Kelvin. It's 342 Kelvin. 342 Kelvin. Can you suppose this is 342 Kelvin? 342 Kelvin. This is atmosphere. 342. This is a case you already familiar with. This. Then what is this value? Recall. What is this value? This is the vapor pressure curve. Liquid vapor pressure. This vapor pressure is also the total pressure. Single vapor. So what is the diagram like? What is the vapor pressure value? You recall. What is this value? Okay, value is expansion, reversible evaporation of water, etc. 0.3 atmosphere. Okay, I am sketching this. Then I will take up some criticality on this. Try to understand this. I am sketching this one. Otherwise, you will not follow. I am drawing curve H2 liquid. This is the liquid water. H2 liquid. Happy? And this is the dots are the H2 vapor. This is equilibrium. This point I am discussing. We call it point X. So X is better. State X. I am sketching. State X. Figure 2. Figure 2. Figure 2. State X. What is this? What is H2O, vapor, right? Vapor. What is the pressure? You know, if this pressure is automatically, this temperature you cannot change. Automatically, this value is 0.3 atmosphere. What is this? pH2O is 0.3 atmosphere. How the system will be under equilibrium? This is our external pressure. I gave you P external. P external. How much it is? This, remember that diagram is what? 0.3 atmosphere. See, P external is nothing but the vapor pressure. The perfect diagram. This point is given sketched by this nicely. Okay. Now what I said, what is the degree of so why you oh, give a thermostat, otherwise what? Give a thermostat, temperature is fixed as what value? 342. Suppose you kept 342, this 0.3 automatically. A 0.3 keeps, then 342 automatically. One of them is automatically on, independently. Now follow this. If you, what is the degree of freedom for this equilibrium? For this, you go water, liquid, water, vapor equilibrium. Equilibrium. What is the degree of freedom? Tell me. Degree of freedom is what? You know very well a moment ago. Two phase coexisting. Once more writing for you. If is C minus P plus 2 quickly. Component is 1. Two phase to 1 degree of freedom. Achha, what does it mean? 1 degree of freedom, you know, understand, sir. I fix temperature with the thermostat. Vapor pressure cannot be otherwise. Cannot be otherwise. Okay. So this. Now I tell you what. So okay. Now suppose you violate. You violate. No, I will not keep sir 0.3. I will make it higher. Higher pressure. So this is okay. Okay. Now next, if P external is the pressure is 0.3, you have not chosen. It is chosen for you. So you are choosing. Now you are no. You are exerting a freedom. You say no. If pxt is fixed, is arbitrarily fixed at any value greater than any value greater than what? 0.3 atmosphere. E.g. 1 atmosphere. E.g. 1 atmosphere. It can be 0.4. It can be 3, even 0.5. 1 atmosphere. E.g. 1 atmosphere. Just 1 atmosphere you may consider easily. Tell me what will happen. So you go by this. So 0.3. Follow this. Follow. You have a fixed 342. What is the equilibrium combination for the two phases to coexist? Is the hot pressure 0.3 external. Okay. Now if you that means you had one freedom, you are satisfied. Okay, I have applied and I have. So if you increase the freedom. Now sir, so 1 to fast. This I have chosen. At the same time I am choosing 0.4, 0.5, 1. That means what? You are actually over exercising, violating the phase rule. Then what is the consequence? You remember this consequence is this. If we exceed DOF, degree of freedom, which is known as F, then what? Phase elimination will take place. Phase elimination, two phase you will not expect anymore. Phase elimination will take place. Important. Will take place. You may be interested. Phase elimination. Why this phase elimination? Can you show me here? Sir, I have chosen this temperature 1 degree of freedom. Then actually this was automatically, but I am not satisfied with automatically. I go here, sir, 0.5 perhaps. 1 I have considered. I will consider 1 also. In the sketch 1 I consider 0.1 atmosphere, sir. Then what will happen? Is it any more liquid vapor equilibrium? Liquid. If you again otherwise also, if you actually don't consider 0.3, it is less than, not only greater than, it is less than also, greater than or less than. What will happen? That means if you exceed this, then what will happen? It is liquid. That means you make it 1. I have sketched that. When it is 1, the vapor will condense into liquid, and again equilibrium. So this is also equilibrium state. This is also equilibrium state. This is if we exceed. If you actually lower the value pressure, external pressure, Okay, then 0.3 atmosphere, then what will happen? Then what will happen? This I discussed in the class previously. If it is less than, not greater than, less than also not permissible. So suppose less than say 0.1, 0.2, etc. Less than, then what will happen? Again violation, again phase elimination. Which phase this time? The vapor phase will be, liquid phase will be eliminated. So vapor will be stable. With liquid will be, this is actually vaporization. This was actually example of reversible evaporation, irreversible evaporation. So this is actually, so right, liquid. So it take place. So now how will I justify the follow this? This is little discussion. I will sketch this. At this part I will sketch. 1 atmosphere and this side. Perhaps I will label. APC minus people. How many you have applied degrees of freedom for this? If you apply for this system 2 component is 1, 2 freedom component 1. What is the consequence of P? How many phases you expect? 1. No more, not 2. Not 2. Not 2. Because of phase elimination. Because of elimination. Phase elimination. Okay. This is okay, so 2. So hence this is actually, so it is actually, we went back to where? Case 1. We went back to case 1. This happens actually. 342. I sketched this also, this 1 atmosphere. Actually, I am running out of, so I am drawing this again. You follow this, please. This is very important because this will actually trigger another question. P is what? P external is what I have done? Tell me. The first is that I discussed. Increase. If I increase, what is P external greater than 0.3? If I mention this, then you will understand. Is what? Namely 1 atmosphere. Happy? Greater than 1. Then what sketch it will be? Can you tell me? This was previously. Now it is 1. So what will be sketch? Sir, all liquids, sir. All vapor will be condensed into liquid. So all liquids. Right here, only water liquid, vapor, no vapor phase. No H2O vapor. No vapor phase. No H2O vapor. Phase elimination. So you are satisfied? Liquid single phase, and single phase, okay, phase is okay. Analysis is over. Okay. My question is now the real question starts. Okay. Acha, I have some problem with this. Next question is, as I told you, now you follow. This is a very critical thing. That's why I said critical issues. Can I remove this part? These are no longer required. This case 1, case 2 all over. And give a star. Don't worry. Yeah, this is good enough. Follow. Give a star here. Will you? Give a star here. Next question is what I am actually doing. You follow this. So this is the situation. I am giving you another situation. See what I am saying. Let me tell you. I am actually theoretical statement. That's it. I am going against this truism that this actually established truth that when it is more than, I violate this degree of freedom allowed, then I lose phase. The system loses phase. But I say I that means only liquid with 2 degrees of freedom. See, freedom. Oh, this diagram is always needs 342K because that is your freedom. That you have chosen arbitrarily. I have chosen because I know the value for this temperature. So you have applied 2 degrees of freedom. I will show you that yes, I will apply 2 degrees of freedom. Still liquid vapor coexist. This is your final, your very useful lesson. How, under what condition? Now we will show. See how both how the liquid vapor equilibrium, will prevail even when F is 2. This is the issue. I am showing you. This is the sketch. In this sketch, you will figure 1, 2, 3. I am giving sketch. How shall I do this? You know, this it always follow this. What? Yes. Yeah. Yeah, you will answer finally. How explain that I explain the elimination by the phase rule. Phase rule says, okay, no, you cannot. You have to eliminate a phase. Equilibrium. Don't think that this is only equilibrium. Don't think that this point is equilibrium. This is the single phase equilibrium, very much equilibrium. This is also equilibrium under this change condition equilibrium. So what I'm saying, I'm sketching this. What I'm doing, you follow. I'm showing. See, I'm going in contrast to this. I'll maintain 1 atmosphere. So before and I'm giving you the P is 1 atmosphere external. P external is 1 and I'm giving you. I'm still writing and temperature same. Don't change unnecessarily. T is 6. What is this? 342. 69 degrees centigrade. What has happened? See, somehow I have to change the pen. 342. So I'm writing one. I'm not showing these cases. Writing H2 liquid, H2O vapor. Yes, they coexist. Even in this, point 342 does not permit any pressure other than this vapor pressure. What is the vapor pressure? Right here, pH2. Right? Tell me what is this? 0.3. This cannot be changed. But still 1. That means who? This is 1. This is 1. That means this is wrong figure. But how I made this? Now introducing inert gas, argon into the system, and argon gas. What pressure it is? Guess what is the pressure for argon? Tell me. To make it 1, is 0.7 atmosphere. Balance. Now it's okay. Now you have 3. You have this. You can. In fact, this is very common. This is very common. In this room, this happens. This room, what is the total pressure? 1 atmosphere. And still, actually, you see, this is a vapor pressure more than this. They don't condense back. Okay? High pressure don't condense because of the presence of other gases. You try to follow with the simple example. Argon does what? Miracle or change. Okay, explanation. Why in presence of argon? You say how it is. Actually, when F is 2. In presence of argon. What F is what? Now explain. That means how many freedom you have applied? Tell me once more. 1, 2, 1. It can be 3. It can be 4. Any value greater than 0.3, 0.4. And what will have it? Still, in principle, it should have been 0.4 exceeded. It was liquid, but no liquid vapor. The F is now see explanation. I'm just starting, but you should. This is giving trouble. Red. This is. Shall I check this? This is. Okay. F is start in presence of argon. Is it any more 1 component system? This 2 component system. F is right first. F is C minus P plus 2. How many components? Previously it was 1, but argon is actually introduced. So it is a 2 component system. And what you get? How many phases? Tell me. Phases. Tell me how many? 1 is liquid, is 1 phase, and 2 gases makes always 2 phase. And this gives you 2. So no problem, no harm. So what are these? Temperature, P means P external actually. P is, this is not good. This P, okay. This is TP. So allowed. Which allowed because component has increased. So that's why you have this situation. This is the thermal. This is phase rule explanation. Phase rule explanation of 2. Phase rule explanation. Is a phase rule explanation. 2 because of the presence of argon. In presence of argon, I introduce another component. This is over. This part actually I don't have to actually dragon on this. Okay, this is so. This you have to be careful. One problem I will consider that you see presence of argon makes a difference. Okay, this is no longer this single component, but this is actually this. This you can do this anything. Now next is what 7th point. Last point. Last point. Last point. Last point is it follows. Okay, I forgot this. I forgot to do this. 7th point. Then let me carry on if I can with this. No, it will happen. This is actually I have to use this one. Then I will see. This 7th point. 7th point. What is this? Last stable metastable. This is actually another discussion. So one discussion is over. It should be your mental block. If you had any, you understand this. Okay. We using the phase rule: stable, metastable, equilibrium. Stable metastable lines in a stability diagram. In a stability diagram. I will show you. I am drawing you once more. What else I can do? This is the temperature. This is the pressure. And typical case, usual case, solid, liquid, vapor. It's better I draw actually. Draw this way. This vapor. Solid, liquid, vapor. Quickly. So you know. So have you ever thought of this? That, sir, this equation I gave you, and I have plotted the equation. So why you stopped here, sir? Why you stopped here? Similarly, I gave you equation. Why you stopped here? And why you have stopped there? Why it has not come down? I am coming down, but dotted for some reason. Because actually I will remove finally with justification. This is also dotted. It goes to where? Goes where? Infinity. These were solid, liquid, equilibrium relationship given, and the plot. This is the plot. And liquid vapor, this has the, if you give a name to the triple point is O. So what is this? As you remember, this is OA prime. This is the OA prime. This is the OB prime. OC prime. These are the extension. So I use corresponding expression. I can give you A double prime, B double prime, C double prime. Please follow me. Okay. This is the curve. Smooth extension. Smooth extension. This curve. Don't stop. Don't stop. Then what you get? Then 6 segments. 6 segments emerge around triple point. Around the triple point. 6. How many curves? 1, 2, 3, 4, 5, 6. Around the triple point. Triple point is known as O. O. Of this, of which 3 stable curves and 3 metastable curves. Always, all diagrams on earth. Even iron, at the end I will give you the iron, PO, P3O4 and iron diagram I will show you. This all, same deal. Same, you will be tired, all, without any exception. Any stability means this deal. Stable metastable and 3 metastable curves. I tell you, follow me, please follow me. That why now metastable should be, have been removed finally. But what is the reason? Which are metastable, sir? How do you know this is stable? Why not this is stable? This is metastable. Why not this is stable? This is metastable. Another property you write. Also note. Stable, metastable, alternate. Stable line and metastable lines. Stable lines and metastable lines, curves, alternate around triple point, alternate around the triple point, around this rule, triple point. Like this, like what? Like how? Stable, next metastable, then stable, then meta, and so on. So see, stable meta. You might argue that, sir, why it is stable? I don't understand. Sir, yes, sir, alternative possible. This is stable, stable, meta, stable, meta, stable, meta. Which are actually stable lines, which are metastable lines. Here, this actually you have to have the justification for this. Just justify this. Okay, stable, meta, and so on. Continue. So two ways have been more actually. You identify. I quickly give you. Achha, what is this equilibrium? Well, I wrote, but I have removed liquid. You don't see actually right here, far away from this. This curve, follow one by one. I am showing you. You will actually satisfied that three ways to convince yourself. So, this is which curve? Concentrate on this solid liquid, so-called stable. I say I don't know yet. Solid liquid. So this region, what does it mean? This is the stability region for liquid, and this is the stability region for solid according to A curve. This I have to show. Rather than write, I show you. I discuss. Consider A curve. What is along way? What happens? So equally stable. Both are together. Solid liquid to the right, one elimination. Liquid stable left, S. So you follow. You see. If you have this stable line over this range, liquid is stable, no doubt. Over this range, solid is stable, and over this range, vapor is stable. This is single phase, and these are two phase. Okay. Now you follow. Stable, actually, right? Another thing, note also, stable lines are mutually compatible. Stable lines are mutually compatible or compatible. Mutually means compatible, or mutually, you may write mutually or not, are compatibles. They are in agreement, and metastable lines are not compatible. Why this? You follow this. Please follow. Why is it compatible? See, first you consider so-called stable line. This and this, see, they are perfectly in harmony and agreement, happy, friendly. Why? According to this curve, this side, this zone is stability for liquid, and according to this curve, another stable, so-called, is what? This one is for which? This is liquid vapor. This is solid liquid. This is liquid. Liquid here, upper is liquid, lower is vapor, and this is together. So upper is liquid. It also says liquid. Okay, liquid stable. It says liquid stable. Agreement, compatible. Similarly, if you work here, it is what? Tell me. This zone. Tell me. According to this curve, what is this curve? Solid vapor. So this vapor, according to this liquid vapor, this is vapor. So in perfect harmony, and you know for sure this is the stable. And if this is stable, alternate means these dotted are metastable and should be removed from the system because they are unstable. Okay. So now again see check whether they are unstable. They are not okay. They are, what is this called? They are not compatible. Follow according to this curve. Tell me. See, follow. This is which curve? Solid vapor. Solid vapor theta. So what is this? Also, this is a continuation of this. That means it says solid vapor, same solid vapor, and this next one, check compatibility. It says this side is vapor stable, and this says this is what? Solid liquid. It says this side is liquid stable. Take a look. Solid liquid. Down solid liquid. Same, because you have to draw. You drew this independently. You do not know what is happening. Solid liquid. This side is according to this liquid. According to this is what? What is this? The continuation of this vapor and class. Similarly here, you consider here this and this also, this and this. You do yourself. What is this? What is the stability region according to this curve? This is which curve? Solid vapor. So this also solid vapor likewise. So this side is solid, and according to this is which curve? This is actually liquid vapor. This is liquid vapor. This upper is liquid. This is a liquid. And this is vapor. Class. So remove this. So hence, if handle is removed, and let me remove this. Actually, before I remove, I will remove. Another way. See, if you want to solve another way to understand this. Okay, very good. Another way, second way rather. This is what is the vapor pressure? Follow here. Why, sir, this line is metastable relative to why this is solid vapor? Solid vapor line is metastable relative to liquid vapor. Why? What is the vapor pressure of solid? If we extend beyond this point, what is the vapor pressure? Any point, any temperature you consider. This you consider any temperature. No, I have no T1. What is the vapor pressure? What is the solid vapor pressure? But this is which diagram? Any diagram, metal vapor. What is the vapor pressure? This is vapor pressure. This is solid vapor though. Solid vapor is solid vapor. Vapor pressure, vapor pressure, vapor pressure, vapor pressure, vapor pressure. Equilibrium vapor pressure. Vapor pressure. For which? Solid. And this is for what? Liquid. And this is solid liquid together. That vapor pressure, that's another story. That is another complication. That is not today. Solid liquid is easy. So, sir, solid vapor, what is the vapor pressure? Marked by this value, say 0.3. Any value, any damn value, say 0.3. And what is the vapor pressure corresponding at this temperature for the liquid? Any value, this is the liquid vapor line. Less than 0.3 means 0.2. If one is 0.3, 0.2, which will survive? Vapor pressure getter means free energy getter. Vapor pressure means focusity. Focusity means free energy. So free energy getter free energy space will be removed. Will be removed, will be eliminated. Okay. So that means this solid, you cannot, solid is a metastable here. Solid vapor line is a metastable line. It cannot be there. That's why this is the vapor. So vapor pressure means, vapor getter means fugacity, means activity, free energy, as I told you. So all getter higher value, higher free energy means sir will be removed. Okay. Okay. This okay. Okay. For to sub removed, and the liquid lower free energy will survive or will be there. So this is okay. What is these two I said? So this is another one. So that's why this will be removed. What else? Stable, metastable. Achha, now I think enough. I have said enough. But this is analogy iron carbon diagram. Analogy iron carbon oxygen diagram. This is a famous, very popular. Here also you get really, you cannot avoid triple point and metastable, stable, metastable. Always any diagram, whole life, anywhere. So iron carbon oxygen, your favorite. What is the plot? You know, famous plot. Any number of ways it is plotted. Percentage CO versus temperature. Because this is the diagram. If I recall, you recall this. This is the stability domain for single phase, namely AP3O4. This is the stability domain for, I am very sorry, APO. This is stability domain for AP3O4. This is AP. There is AP2O3 also, but it is not shown, not typically, but it is here. We are not concerned. We are concerned on the one system. Again, you see, sir, 3 lines. No, you will say, no, there are 6 lines, 6 curves. These are stables are shown, metastables are where? This is the triple point. This is the triple point. So this is the, this slightly curve, upward curve, slight. Not, so this will go same way. Smooth extension is the metastable. Smooth extension is the metastable. Past the triple point. Past to the triple point. What is the metastable here? Sorry. I think good enough. 6 segments, alternate, all clear, stable, metastable. And now I'll tell you here. Here actually you can very easily follow that compatibility of free energy also. Compatibility, you can check compatibility easily, 2 ways. But this will be totally, this is last topic. And for this, then a problem. So, the answers, because I have already given you 6 segments. 2 ways I will tell you. First, compatibility checking. Compatibility and or incompatibility checking for metastable or compatibility for stable. This check what it says. This curve says this side is, this zone is stability for APO, but this is APO. Shall I write this for you? This curve is for what? This is AP, solid liquid vapor. This is what? This curve is what? Tell me. APO, AP3O4, and this curve is what? Tell me. This is, I am writing here. AP3O4. And this should be ABC, AB, BC, AC. Okay. So very good. Now tell me. According to this diagram, this is the who's stable here? Out of yes. Yes, out of this, who will be stable here? Here along this curve? Both coexist, sir. They are in equilibrium. The whole thing is equilibrium. But single phase equilibrium or two phase or three phase, sir. That is your problem. So anyway, so it will coexist. I just have at times actually check. So now tell me, which according to this sketch, this region is stability for what? Follow this curve, APO curve. What is the stability according to this? APO to this. Remember, this is APO stability, and then this is the stability. It also says APO compatible. This also says this side is AP3 pole, and this also likewise AP3 pole. So you are fully convinced. Let us see what does what do these metastable segments do. Start. What is this? This is which line? Remember, this is actually AP3. So this side is what? Is AP3 pole. That means this is also AP3 pole. So this is AP3 pole, and next is what alternate, not this one. This one. This also says what? This side is AP. Is it? AP to see here. AP means AP. So this is APO, and this says what? This as I told you. What is this curve? This curve is AP3. This side is AP3 pole. This is APO. Class disagreement. Okay, incompatible. So you remove these lines. Okay. Another way, second way. Here very interesting. You follow free energy number of ways we are talking. Vapor pressure, fugacity, activity. So see, free energy greater or less, delta G is negative. That same thing showing in many different ways. You tell me what is the activity. You please, I will tell you what. I'll compare these two. Follow this. This is which curve? Remember, this is actually, remember. Shall I a little bit exceed? This is what? Which curve? I should repeat. Repeat. This is AP304. Upper is AP. But this is like this. Huh? This is AP304. Okay. Now tell me what is the activity? Question. AP solid, AP3 equilibrium with CO2. Everyone knows. 3 CO is 3 AP plus 3 CO2 as a function of temperature. Okay. Please follow. Tell me what is the activity of, follow me, activity of iron. If you consider this is actually, okay, you consider this metastable line. What is the activity of iron along the curve? On the curve, is AP3 coexisting, and AP is pure. AP is pure. Both have activity 1. So activity of AP, not vapor here. Okay, vapor is actually discussed there. Here solid activity, solid iron. Pure solid iron has activity of what? 1 with respect to solid iron. So activity iron is 1. And what is the activity of iron here? This is 1. And what is, according to this diagram, what is the activity here? According to this diagram is what? This diagram is what? AP, tell me, AP, I have written there. So activity of AP is where? Here. So repeat, AP, activity of iron and activity of AP is what? 1 each. Here up, above, activity of iron is 1. AP is not there, means not there is what is significance in terms of activity? Less than 1. That's why I don't see. Okay. So okay, very good. So activity of AP is 1. So AP is 1. What is the activity of iron? Here, according to this curve, this point, what is the activity of iron? This region. According to this curve, here 1, all 1. Why 1? It is iron stable. 1. And here, AP is stable. But iron not. Why? If it were 1, then they would be together again. Always together. So it is less than 1. And this curve said what? This point, what is the activity of iron? 1. This curve, AP I have written for you. AP, what line? AP 1. So this activity is 1. Metastable 1 gives 1 activity of iron, and stable gives less than 1. Means activity means equated to free energy. So free energy is greater with metastable and less with the stable at free energy. So if the free energy is greater, then that means what is the indication that free energy, that phase will be eliminated. So it gives 1, it gives less than 1. So the one which is higher free energy curve, that will be eliminated. So these curves will be finally eliminated. You will check another one quickly. You will check here this and this. What is the activity? This side this side and this side. What is the activity of which we would consider convenient? Which one? Convenient one should follow. This is below is APO, is it? APO. APO. This is carried down here. APO. So this side is APO. So right. APO. You may forget APO. And what is according to this? What is the activity of APO? Check. Answer this yourself. I've given you what is the activity of APO. This side 1. I'm written in bracket. 1. According to this dotted curve, etc. 1. And according to this one, yes. Why? On the line, what is the activity 1? Above who? APO 1. 1. But below don't see. Means that's why you don't see. So APO less than 1. So it is APO 1 and less than 1. Which will survive? Which will this will actually eliminate. This will stay there. So that's why this is the stable line. So now after this is you have understood this, eliminate this from the diagram, and you have this nice diagram. Okay, this is your similarly. So this all over. This is the discussion part is over. I should not carry on. Okay, I wanted to discuss these points. Okay, another point will come when in the problem solving. Okay. So good, very good. So next point is how much time?
1 hour
1 hour 20 minutes left. Oh, so 40 minutes or so, roughly. Close to 2 hours. Oh, close to that, 35 minutes, 40 minutes. We can tell it. Now, let us take up. Now, enough of discussion, enough of analysis. Next is problem. Shall I remove this? This I can remove. With your permission? No, this is better. I don't know which is better. All remove. All remove. Phase equilibrium continued. Just keep retain the title. Phase equilibrium continued. But this is your assignment problem. Straight into the assignment problem. No practice, etc., etc. This is not needed. So assignment problem. So what shall I write here? Assignment number. Next is assignment. Go slowly. Not very slow though. 40 minutes. I say how many I can cover. Number. Guess 8. 7 over. This is 8 coming. Assignment number 8. Based on phase equilibrium. So problem 1. Problem. Let me write this side. Problem 1. Assignment problem. Quick. Let me write. So the vapor pressure of solid zinc. I have to. No way. You have to write the vapor pressure of solid zinc varies with temperature. Varies with temperature as LNP atmosphere. This is gas scale problem. I'll write somewhere. At the end, remind me. This okay. LNP atmosphere minus 15,775 by T minus 0.755 LNT plus 19.25. Any difficulty? No difficulty. Do you recognize this? Anyhow, recognize this relation? Today, first, number 1, A plus B by T plus C LNT, okay? It's okay. And similarly, and the vapor pressure of, continue. Problem is continue. The vapor pressure of liquid zinc. Liquid zinc, you know, very good. Liquid zinc varies with temperature. Varies with temperature as, again, LNP atmosphere. Pressure in atmosphere is minus 15,246. 15,246 by T minus 1 point, you know very well, what is 1.255 LNT plus 21.79. Happy? This two. Now calculate. Given this, calculate 1 by 1. A. The normal boiling point of liquid zinc. The normal boiling point of liquid zinc. Very good. B, the triple point temperature. The triple point temperature. C, the heat of evaporation of zinc. The heat of evaporation of zinc. Zinc at the normal boiling temperature. At the normal boiling temperature. D, the heat of fusion at the triple point temperature. The heat of fusion at the triple point, what is this? At the triple point temperature. At the triple point temperature. Happy? E, fifth, Cp Zn liquid minus Cp Zn solid. Zn zinc solid. Cp Zn solid. The right here gas scale from gas scale. Dr gas scale. Dr gas scale. Gas scale, second edition, page 182. We worked out an example problem. Worked out problem. But this is very instructive problem. So these are the I draw something here. This is all over. Can I box this so that it helps you? Just I for your reference, I am sketching this zinc single component cups. Zinc single component. What is this cups like? You know, what is zinc solid? Solid means zinc solid. In fact, liquid, vapor, pressure, single component, pressure, temperature. Very good. Zinc solid, zinc solid, right here. Zinc solid, zinc vapor. Right here, solid. Zinc solid, right here. Zinc solid better. Zinc solid, zinc liquid, zinc vapor, single component. Now, you follow this. Which are given to you? This is a triple point O. Give a name to this in case we are interested. Where here? OA prime. A prime I shall give here. OA prime, OB prime, OC prime. As before. All as before. What is followed? What are the given? This equation is what? First one is what? This is for vaporization of solid zinc. That means this cup. This is a solid vapor. Three term. I gave you three term today. Likewise, this is for what? Obviously, this OC prime. These three cups. Nothing else given. Nothing else. No calculate. Normal boiling point. Can anyone tell me normal boiling point? How to solve the normal boiling point first? Solution. Good boy. What is normal point? The boiling point corresponds to 1 atmosphere. Vapor pressure. That means what will be the normal point? Shall I sketch here? I may. So I will show you. This is the 1 atmosphere line I am drawing. 1 atmosphere line. This is the temperature you have to find. P is 1 atmosphere, right? 1. And here, right, atmosphere. So this is the volume. This question. What is the temperature? This is the temperature. Actually, is okay. Happy? So very good. So this. Also, let us how you get this? Very easy. This is a liquid. Boiling point means liquid vapor reference. No solid vapor. Sublimation. No melting. Solid liquid. So this is what is the how you get this? See this is the equation for this OC curve.